everyone. Recently, I made a presentation entitled How to Explain General Relativity to a Young Person. And now I would like to present the Addendum A for that presentation and entitled Minkowski Method in Detail. In this presentation, I'd like to do first of all, a quick refresher on the geometry of flat spacetime. Flat spacetime is the relatively flat, not very much curved spacetime corresponding to cosmically small masses, such as the mass of the Earth, the planet Earth. So I wanted to produce a refresher of spacetime, flat spacetime, which also applies to for which special relativity provides a very good model. And I want to, in that refresher, produce the invariant, which is the interval between two successive clock times. So I'll show you on the diagram, but we'll cover that. And then we're going to do what Minkowski, well, Minkowski never told us that he did, well, I didn't see it, put it that way. I've never had any physicist even on the YouTube show me how they do all the steps of the Minkowski method, which I think is a problem. That people think it's a spoon feeding to give all the little steps, but if you never show them, people tend to just jump over it and accept the result, and in that manner they don't necessarily get the full detail of the understanding. So today we're going to delve into it. And the first step, as it turns out, of the Minkowski method, according to my particular view on it, is to multiply the entire expression for the invariant by -1. Which maintains the arithmetic truth. For example, and I mentioned this briefly in the previous presentation, you can take 2 plus 2 is equal to 4. Well, if you multiply, and you just do it on one side of the equation, -2 plus -2, you get -4, and -4 is not equal to 4, so you have to multiply both sides of the equation by -1, and then you don't change the essential nature of the equation. So you have -2 plus -2 is equal to -4. So we're going to go and apply that and see where it takes us. And it actually takes us somewhere actually kind of amazingly, interestingly, and useful. So I notice here I say -1. I'm not saying the complex number I or anything, at least not yet. Because I think that's the best place, and the clearest way to start this thing is just multiply both sides by -1. We do that very often, and it's nothing mysterious. Okay, and then the next step in the process, as you shall see, is to replace the square root of -1 by I. Now, by I represents an operation. It's a simple rotary operation. Basically, you take, and this is the point, this is the direction, and if you multiply by I, you rotate the direction 1 quarter turn to the left, by convention to the left. I is no more or no less than a quarter turn to the left. Okay? Now, if you take that I applied to this length, and you apply it again, it goes another quarter turn to the left. So the first one was 1 quarter turn. Now you do it again, or I times I, or I squared, is 1 quarter turn plus 1 quarter turn. It's a half turn. Now we know this as a 180. And a 180 on the highway, let's get grounded here. You're driving along and you realize you're going in the wrong direction. So you want to go the opposite direction, right? You want to go negative in the negative direction. So you do I times I. You apply the operator I times I, which is I squared, and it's like multiplying the direction by -1. And for that reason, people say, rightly, within the context, the right context, that I squared is equal to -1. But don't forget for a second that the operator called I is no more or no less than 1/4 full turn to the left, which is counterclockwise. Now, so we're going to make that substitution. Next, we're going to discuss how these arithmetically sound operations, like we do multiply an expression by -1 and on both sides, we know what the result is. And we know what replacing -1 by the square root of -1 by I. Well, why the square root? Okay, let's start with this again. We multiply it by I, you get this rotation. You multiply it by I again, you get that rotation, that particular result. Now that's R times R. So the square root of that operation is going to be just R. And let me do that again. R times I, R, the square root, is equal to R. Now why am I saying R all of a sudden? I mean I. I times I is equal to -1. Well then, the square root of that, I times I, the square root of that is just I, which is this direction, a rotary operator, okay? So the square root of -1, which is this, is equal to this, okay? Which is I. It's the operator I, 1/4 turn to the right. Let that sink in. These things are, I is no more and no less than 1/4 turn to the left, applied to a direction, okay? So then we'll discuss how these arithmetically sound choices produce Minkowski's specific form of the invariant expression. Now Minkowski wanted to put the expressions into an arithmetic form that was easy to manipulate by mathematicians and mathematical physicists. So it was very important in Minkowski's view to put the invariant in that particular form, which I'll show you. I'll derive it for you, so that the mathematical model would be easy to manipulate and even easy to explain. And Einstein, incidentally, he really fought the advice of his good friend Hermann Minkowski to use this form. And it could actually be because it's such a simple thing. Like people say, well, you just substitute blah 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 by I, I times something, and if you don't go through it, I'm not sure that people really understand it. So maybe even Einstein didn't understand it at that point. But I feel a lot more comfortable with Minkowski's method after having gone through what I'll show you next. Okay, next in what we're going to do here in this presentation is we'll show that Minkowski's form is fully consistent with the momentum diagram geometry as it is originally shown. So there's a particular kind of geometry that is basically native to the way I look at this thing. I like to think in terms of shapes and rotations, and I find it incredibly useful. And also, like when you'll see I use colors in some places because the eye can see it all at once. I like to see mathematics in a form where I can see it all at once, bam, like instant perception, and expressing equations geometrically allows you to see it all at once, and it's good. Sometimes at night I like to dream about it, both when I'm slightly awake and both when I'm completely asleep, and to have geometrical representations of mathematics. It's far more easy to import into the dream world and It's a wonderful thing, actually. It's one of the reasons I'm in love with this sort of thing. Didn't start out quite that way, but the more time I spend with this sort of thing, the more actually thrilled I am with it. So let's go now, and I'll tell you. This looks like a busy diagram. It's busy because I haven't skipped any steps. This is like the ultimate spoon feeding. Now, a lot of people discourage spoon feeding as if it's something so bad. But if you look at the kitchens in the world, there's a lot of spoons there. Spoons are very useful, and people use the spoons to feed themselves. So spoon feeding is not such a bad thing, you know. And I think if there ever was a time to spoon feed right now, it's with the Minkowski method. Because it seems that so many professors even and teachers, they don't want to deal with this Minkowski, so they take a shortcut and skip right over it. And I don't think they understand it in its full richness, and the justification has a little bit of mystery in it for them, the way that it's typically taught. So I'm going to teach it a different way, where there's no mystery except the mystery of physics, which that beautiful thing will hopefully never go away. It's so wonderful. Anyway, so we can see here, what we see here are what's represented as three momentums. The momentum traveling in the red line, which is associated with a clock, the motion of a clock. Now, a clock has a momentum, and everything, it turns out, moves at the speed of light. And I proved that in general relativity expression video number 1. And it's not that the magnitude of the speed ever changes, but the direction changes. So here we have a momentum in these two charts. I basically copied this one and presented it again because I wanted to show two observers, and to show that they two observers agree on the invariant, and we could easily apply a third observer, and they would all agree on the invariant. And what the heck is the invariant? Well, the invariant refers, so we have, well, let me say, we got an observer traveling in the direction of the blue line, and we have an observer traveling in the direction of the green line, and an observer traveling in the direction of the red line. And the red line corresponds to an observer that has a clock. And the observer notes the clock at the the point where all these lines cross, in this case, and the point sometime differently, after some time interval, hg has passed. And people here we're dealing with reality. Now, if you just think about it from what you know about reality, everyone looking at the clock at the position h on the timeline, the red timeline, it has to agree at what the clock says. I mean, they could take a picture of it at that point, and they will see the time on the clock. And then after it's gone from H to G, any observer can take a picture of that clock, and they'll get the face of the clock at that particular interval. So they take what the clock time says at time G, and minus what the clock time says at the time at H, and they get the time interval. That is the invariant. Now, why does Einstein call it the invariant? Well, because everyone must agree on that interval, because it's two instances of a clock face that shows two different times, and since it's in physical reality, and it's not subject to whims or imagination, it's physical, everyone's going to agree on it. Okay, so he wants his model has to agree with it. So I want to also point out here the right angle, this right angle. Now I'm going to talk about this in another presentation, because it's a very, very wonderful, quite clear, but very, very deep concept that actually has to do with quantum mechanics. And I don't want to mention anything of that here, except to say that we will nail exactly why that we have to have that right angle here. Now, the use of the right angle is and it's in terms of the geometry of this thing. Let's talk about the green man, the man traveling on the green timeline. Now, I have to kind of define the terms, what they mean as I go along here. And timeline, why did Einstein call these timelines? Well, it is a fact that every momentum has to travel at the speed of light, including mass, okay? So here we have, it could be someone riding on the green timeline, okay? Green man, or woman, but green man, let's keep it simple. Travels from H to B, okay? Now, at B, green man looks over and takes a measurement of, and maybe a picture, a photograph, at the time, according to him, the time when he's at B, what is the time over on the clock? He wants to take a picture of it. Well, it turns out that from physically, to get that now moment for B, you have to draw a line from B to G where there is a right angle between that line from B to G and the red line, which includes H and G on it. It has to come in at a right angle. And it has to come in on a right angle for all observers. It's a fundamental requirement. And I'm going to show exactly why, precisely exactly why, in detail in my next presentation. But for now, I just want to express that needs to be the case. Now, there are explanations I've seen in the video webland, and the, what do they call it? Well, YouTube and things like that. Public media. There are explanations, but they don't say why. They just give a crappy little explanation. I'm not going to do that. I'll save it for my next presentation. But what I want to emphasize is that when you do this, the correct answer always has to have a line that intersects HG, or the line that contains the interval, the timeline that contains the interval, has to, for any arbitrary momentum, like the arbitrary blue man and the arbitrary green man, which can change, the angle is also arbitrary. Now, I want to say that the angle between the two vectors is the speed between the two vectors, the relative velocity. It never these momenta never change their magnitude, but they can change the direction. That's the only freedom we have. And the particular angle between, for example, the green, that's tricky, flipped. The particular angle between the green timeline and the red timeline is the velocity between the green timeline and the red timeline. The relative velocity. That's why Einstein says, there's only such a thing as relative velocity. Well, because the other velocity is constant for everything. It all travels through the vacuum, undulations within the vacuum at the same speed. We can prove that. This is speed c. And when you use balanced units, c naturally is equal to 1. So the majority of physicists will use 1 as a speed for c. Now I find this, it's kind of, when you draw these momentum diagrams, it's very natural. It almost automatically takes care and makes c 1. Because you're putting distance and time on the same footing. It's obvious that it is the same footing. Look, you got the timeline here, that's time, and then you got distance, and it's all fitting into the same diagram. And to do that, the scales have to be the same, so it's going to be c equal 1. I show this in such detail on general relativity 1 through 7. So if you need more, you can go there and find it, especially in presentations 1, 2, and 3 at this level. So I'm going to show here, notice I have this triangle H, B, and G. Just as it's shown, which corresponds to the lines for expressing the relationship between the clock timeline, the red line, and Greenman's timeline, the timeline that contains H and B, where B is an arbitrary point that connects to the now. It represents the B is what position is on the clock timeline corresponds to the point B, which is a time. It's on the timeline, so it's the time that's passed between H and B. What's the time now for Greenman? Well, to find that over at the red line, okay, what's the time now for Greenman at point B? Well, you have to draw a line from point B to red line's timeline, the clock's timeline, and have it intersect at a right angle with the red timeline, okay, and at a right angle. And when you do that, you get the intersection at point G. That's relative to to Greenman. That's the time now for Greenman at on the red timeline. Okay. Now, if you look up, you say, well, I can notice once I got that, I extended the red line all the way out to the point A on blue man's timeline, right? And then you can say, well, what's the time over on the red timeline, the clock's timeline, for A? What's A's now over on the red timeline? And to do that, just like you had to do for the green timeline, you take a line from point A all the way over to the red timeline and make sure it intersects at a right angle. And when you do that, you go, wow, because that resulting diagram now has two right angle triangles. You have H, B, and G in pink. Again, so I'm using colors so you can see it all at once. Boom! You don't have to go H, B, G, think about it. It's the pink triangle. Okay, and then you can look over here and you can see another right angle triangle. They're both right angle because you have to do that to get the proper nows over at and the red timeline for green man and blue man, right? So let's look at this. You can see here A, G, and H is that other right angle triangle. The right angle triangle for the blue man. Okay. So now we have some expressions, and we want to know for both these triangles, what is HG? What is the length HG? Well, for the green man, the length HG, since this is a right angle triangle, you take the diagonal squared, it's Pythagoras, take the diagonal squared, HB, and you take the adjacent side, which is BG, right? And you take HB squared minus the length BG squared, and that's going to be equal to HG squared. That's Pythagoras theorem, okay? So we want to write that down somewhere. So observer time, do it in blue up here in the top, okay? It says H, it's up here. I even give some little hints because I want to make this so simple. I want to do the most thorough spoon feeding ever on this topic, okay? So you get every last little bit of the nutritious value of Minkowski's method, and there's a lot to it. A lot of nutrition from a very small amount of processing here. But I don't want to miss anything. So here we go. I spoon feed you HA squared. So HA squared, which is the observer time right here, HA, squared. Okay, so that's what this is. So I have it both as just HA squared, that length, and I have it as a name too. What is it? That's the observer 1's time for at point G, right? It's going to be A. HA is that time when the clock interval has gone from HG. Alrighty. So then I say, so I do it in blue, and what I say is that the observer time HA squared minus the now minus AG squared. Oh, that's AG. So which is now AG is a distance. It's the distance from A to point G for the now line from point A over to point G. Okay, it's a distance. So if you take AH squared and subtract this distance AG. Now AG, I have shown it in blue. It's a distance. And we know that every distance has, because it's space-time. I've already covered the time aspect. But for the spatial aspect, this distance, AG, which is in space, you could orient it so there'd only be, like, you draw a Cartesian coordinates on it, and you can line it up so it just fits one direction. So maybe it would be x1 then. You'd only have to put x1. But in the general case, x2 and x3 are not equal to 0. And so that distance can be expressed as the square of each of the components. And by the way, these distances are distance squared, right? So the distance squared can be expressed as the sum of the square of the components. So you have delta x1. I leave the deltas out. Einstein, if you look, he leaves out so much in his notation. So I'm just asking I get sick and tired of writing delta, delta, delta. It clutters up, and you don't need to. These x1 and x2 and x3, etc., they represent small distant increments, okay? So this distance, AG, we can express as, for the blue man, x1 squared plus x squared, 2 squared plus x3 squared, okay? And then also the same thing for the green. When I changed the color green because I'm now referring to the green line according to Green Man, right? He's an observer, 2 different observers. And we get the same thing there, that this distance hg, which is the same, say hg squared. Yes, yeah, that's right. hg squared, no, this is not. This should be hb squared. Okay, I like that. It's actually good. hb squared. B squared minus, okay, good. hb squared and bg. Yes, same thing. It's good when someone presenting something makes a minor error, and this is like a typo, because when somebody does that, it kind of wakes you up. Oh, you made an error. What's going on? Oh, what's wrong with that guy? Is he a little bit losing it today? You know, you gotta laugh about such things, but it wakes you up. That's what's so good about it. So I just woke up here. Like what we did with the blue man, we're going to do the same thing with green man, moving on this thing. And so this interval, time interval hg, is if you want to get that time interval squared, and here it is, I wrote it here, the red line, say time interval hg squared, right there it is. And see that equal there, and I say equal here, so I'm saying that each one of these equals the same thing, okay? So let's go through this one here. hb squared minus hg squared is going to be equal to hb by minus bg squared. You see why I did the mistake in the first place. Let me say that again. hb squared minus bg squared is equal to hg squared, right? So there's the time interval hg squared, and here's the observer time, which is hb squared, minus the distance, this distance here, bg, and I say bg squared, it's also the square of the distance, it's going to be equal to x1 squared plus x2 squared plus x3 squared, because it's three-dimensional space. Remember, in this, we're just talking about spatial distance in this case. So this expression is very powerful, because you notice I have two arbitrary observers, and they both make an observation, and they both agree on the time interval, because they can take measurements of the clock face at h, and they can make measurements of the clock face at g, and that measurement might be as simple as a photograph. And they can take the difference of the two times as recorded on the local clock, and that's a physical reality. It's a physical measurement. So everybody has to agree on that physical measurement. And this equation is what defines it. So this is the first expression. And I've done it for two different observers, the blue man and the green man, because I want to show that it's true for one observer, it's true for the other observer, and by extension, and since these first two observers are arbitrary, the angles between them are arbitrary, it's true for all observers. And so this is an expression. The time interval hg squared, down here, time interval hg squared, which is this distance, it's a physical property. It's a measurement, physical equipment. So everyone has to agree on that. And that is the invariant. Since everyone has to agree on it, no matter how they're moving, in this case we got two observers moving differently, different directions in four-dimensional space-time, shown as in this chart, okay? They agree. So, and since they all agree, it doesn't vary based on the observer, right? So we call that, and Einstein called it, the invariant. In other words, the thing that doesn't vary. So there we have it. And everybody should be happy with that. Then along comes Minkowski, and he wants to multiply this expression here, this whole expression. He wants to multiply by -1 across the board. He never said that in a way that I could find him saying that. But that's what he did. Now I'll prove it. Okay. So let's prove it by multiplying by -1. Now notice here what I'm asking you to do. I'm asking you to open your mind, and we're going to multiply an expression cross on both sides by -1. Now that's not asking too much. I know that you look at all this and you go, "Ooh, it's so complicated." It's really not. It's just I don't want you to miss the goodness. So anyway, let's do it. Multiply across all by -1 per Minkowski. So I multiply, let's go up here on the top and just look at it. See, I have the same expression again, but except I put -1 in front. And then I put -1 in front of the next term. See, put -1. And then the last term, because both of these equal this, right? So this last term, I have to multiply it by -1 too, as well. And I did that, okay. Now here it starts, it was supposed to be totally obvious and everything, but it starts to get a little bit interesting. Because, so we have the expression here. Yeah, but I jumped the gun on this one here. I'll tell you what I did. See here, when you have a bracket, a term in brackets, and it's squared, all of it, the whole bracketed area is squared. When you take something that's out times the square, it's multiplying it, and you move it inside the brackets, it's going to get squared. Which means that when you move -1 inside the brackets, it then gets squared because of the exponent here too. So in order to keep the equality, you need to take the square root of -1 and put it, when you put it inside the bracket. And that's what I did here. I put the square root of -1, which is none other than I, right? Remember you took I, you take this direction here, and then you rotate it by I, and then by I again, and it goes -1. So I squared is the -1 operator. So we're going to replace very properly when you move -1 inside the square root of -1, which is I. Okay, I've shown you that 3 times now. So it's nothing mysterious, that part. So what do we get here? Well, since I did that here, and I can also do it with these -1s on the outside here. Well, we can't do it here. I'll show you why. See, this says negative times -1, negative times -1. So these two negatives cancel, and you get a positive. So that's we got that here. Okay, positive. But these two ones here, I haven't yet popped them inside. So let's do that. We put them inside the brackets, and it becomes the square root of -1, because it's going to be squared, and then it'll become just -1. And that's I. So we put I there. I times observer time. And down here, I times observer time 2, referring to these two, the blue and the green timelines. Two momentums going in different directions. Now, maybe I didn't say this yet, but I'll reiterate if I did. The direction that a particular mass or a particular momentum is moving is what the direction we call time, because we experience it as time. For example, we are masses moving at the speed of light through space in the direction of our time, and we experience that motion in the direction of our time, as a, this sort of thing, motion, aging, which is another form of motion if you really think about it, molecular motion, molecular substitution. The individual atoms don't age. Neutron doesn't. Proton doesn't age. Doesn't even degrade. But its position changes, so it's motion. So here we go. We put -1 inside the brackets, and we got I. We had to put a square root. So, and I've already. The time interval hg here, we've already expressed that as I times the time interval by moving -1 inside that bracket. And so what we're going to do here is we're going to do something which is just a name game. We're actually going to do nothing. But some people, like for example, some people have, everybody that I know of has two names. They've got their first name and their middle name. Well, here we can use a middle name, and it doesn't change the person, right? So I'm going to do that here. I'm going to talk to it according to its middle name. So see here in the for the blue man, I times observer time, that's right here. We're going to call it x4. X4, that's its middle name. And for this, along this green line, that time HB, we're going to call it I. We're going to, for that, which in the expression we get I times observer time in green for that guy. We're going to express it as a green X4. It's his X4, okay? His X4, his middle name X4, okay? So we're going to apply that. What we then get is that X4 squared plus all these squares is equal to, it refers to the invariant Hg, which is invariant, so it must be equal to X4, which is I times the observer form in green here, squared, plus the distance, which is 3 components, x1 squared plus x2 squared plus x3 squared in green, because it's talking about this guy, his variables. And that then we can write as, since it's x4 squared plus x1 squared plus x2 squared, blah, 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 we can clean it up and get rid of the brackets, and that's equal to this, x1 squared plus x2 squared plus x3 squared plus x4 squared, okay? And likewise, we can do the same thing here. And that's why Minkowski did all this, because he wanted this form, which is x1 squared in green plus x2 squared in green plus x3 squared in green plus x4 squared in green. And that's going to be equal to, we're going to do the same thing for this time, which is then becomes x4 for the red guy. And that's equal to the invariant. So I take that from here, and these two things, and I express it down here as the invariant. Well, I put it in black now, because I'm saying for everybody, for all inertial. In other words, you notice these things don't curve. They're not curving. This is special relativity, and there's no accelerations in special relativity. And that we go talk about that in the general relativity section, and even in the previous presentation for young people. We did go on and explain the rest of it in terms of general relativity, and we derived Einstein's stress energy, Einstein's field equation, relativistic field equation. We derived the whole thing. So that, if you want to go that, and designed to be taught to young children, that's my previous presentation. You could tell I got so much in my mind, it's kind of getting funny. But that was how to explain general relativity to a young person, my previous presentation. So here we are down here, and we can rejoice because we found for any observer, x1 squared plus x2 squared plus x3 squared plus x4 squared is equal to x4 squared along the clock interval. And that is an invariant. That is an invariant. And that's what Minkowski wanted. That's why he multiplied across the expression by -1. Didn't change the property. Did not change the property of the expression. And it derived specifically from this geometry. This geometry we have shown with the very simple geometry. Beautiful, beautifully simple. And this particular geometry I'm showing here, where we have a right angle along the spatial line AG and BG and AG, that intersects with the clock timeline, the red one, at a right angle. It's predicated on this having a right angle on the distance dimensions for these two observers. And since I picked these in a general way, it's a general result. It's an invariant across the board, and that's why I put it in black, because it applies for any observer, any inertial observer. And that's equal to x4, which is squared, that's this interval hg squared. And that x4 squared is the invariant, and this is what it's equal to. So that's what Minkowski wanted. A beautiful, it puts the mathematical form of four-dimensional space-time onto this very similar form of the Pythagorean Euclidean expression, which applies to three spatial directions rather than four. And x4 refers to the, in this case, I times the time interval, hg. But let me just say again, it's not referring to a different geometry. This is the key to the understanding of this thing. And what we did is we just threw, first we put an arbitrary clock traveling along this arbitrary momentum line, direction, okay? The speed is not arbitrary. Speed is a quantity, it's not a vector. And that quantity is the speed of light, c. Okay, and c equals 1 when you put it time and space on the same footing, which Einstein did. C becomes 1. Okay, so that geometry, this simple geometry where you put these three arbitrary vectors down, and one of which has clock on it, and then you find that they all agree on the time interval, okay, according to this expression. x1 squared plus x2 squared plus x3 squared plus x4 squared is very similar to what we get in Pythagoras, where you get x1 squared plus x2 squared plus x3 squared is equal to the diagonal squared. Puts it on that same familiar footing. And after going through this, I can really, in this detail, I can really appreciate why Minkowski did this and how it's not really messing things up, because you're just doing very obvious arithmetic substitutions that don't change the essential nature of the expression. Okay, so let's review where we've done where we've gone. Yes, that's right. Today, and see if we've achieved our objectives that I talked about in the beginning of the presentation. So, Addendum A, Minkowski method in detail. What we wanted to do were these things shown. I want to see if I left something out here. Show the geometry, blah, 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 blah. Yeah, I got them all. And let's see, quick refresher on geometry of flat spacetime to produce the invariant, which is the interval between two successive clock times. Yeah, we did that. Okay. Multiply the entire invariant expression by -1, which maintains the arithmetic truth. And I could have said also maintains the essential meaning of the expression. It doesn't change it. And so, yeah, we did that. And I talked about it already. Here, number 3. Oh, I should use my arrow so you'll know what I'm talking about. Yeah, number 3 here. Replace occurrences of the square root of -1 by I. Yeah, we did that, and I described, and I even showed you with this thing. I showed you with this thing. Whoa, I've got to use this hand. Woo! I showed you with this thing what it means and why it's okay to make that substitution. Why you have to do that. Show that the arithmetic choices produce Minkowski's specific form of the invariant expression. We demonstrated that by going through, like in the spoon feeding method, which, by the way, I endorse spoon feeding, especially under the conditions like this. We went through without skipping any steps and showed that the arithmetic choices that we discussed produce Minkowski's specific form of the invariant expression, and it doesn't change the geometry, which gave rise to the initial expression, and it doesn't change the essential character of the expression either. Okay, it's just putting in a specific form. And now, last point, show that Minkowski's form is fully consistent with the momentum diagram geometry as it is originally shown in this presentation. And I did demonstrate it, because I showed that starting from that specific diagram and we come up with a particular expression, and by performing simple algebraic operations on both sides of the expression, which does not change the basic character of the expression, we can put it in Minkowski's preferred form. And I'll even go back here and show you that preferred form again, which is x1 squared plus x2 squared plus x3 squared plus x4 squared, in the most general sense for all inertial observers, is equal to this x4 squared, referring to the time difference on a timeline referring to one that has a particular clock moving in the direction at the speed c, according to that clock. And the interval hg, where the interval hg is shown to be an invariant. Okay, so going back to the end there, we achieved all of these objectives, and it was a delight. Let me just say, a true delight to explain this to you. And it's such an important sequence of thoughts to be able to hold in your mind, so that you can understand Minkowski at I think a very deep level, both from a geometrical point of view, the geometry of space-time, and from an arithmetic point of view. So you can see exactly what he did, and without skipping steps and without making mistakes, and basically having a deep understanding of that process. And with that, thank you very much. I've had a really good time presenting this to you, and I hope you enjoyed it, and I hope you walk away with a little bit more understanding. And that would be great. So with that, I'm going to sign off right here. Bye for now.